All right, so here we have an example to apply what we just learned. So let's remember, first of all, when an object is cooling, we expect it's going to follow the following convention, the following model. So let capital T be the temperature at any given time as a function of time. And we expect the temperature at any given time to be equal to m plus c times e to the negative kt. So this is what we just derived in the previous segment, and where m is the temperature of the surrounding medium. So m is the temperature of the surrounding medium. Again, capital T is the temperature and lower t is time. So here we have a bottle of lemonade at room temperature at 75 degrees, and it's being placed into a refrigerator with a temperature of 38 degrees. Half an hour later, the lemonade has cooled off to 60 degrees. How long will it take for the lemonade to cool off to 55 degrees? So here it's being placed into a refrigerator, and it's kept in a refrigerator. So while it's cooling, it's in the refrigerator. So the surrounding medium for the purpose of this problem will be the temperature of the refrigerator, because that's where it's kept and that's where it's cooling. And so let's do a very simple graph here to represent what's happening. So let's see, the x-axis will represent the time, and the y-axis the temperature. So we have an object that's cooling off in a negative exponential pattern. So very roughly speaking, this is what the graph might look like. And here I'm going to put a horizontal asymptote. Eventually, the lemonade, as it's cooling, it's going to become eventually the same temperature as whatever temperature the refrigerator is kept at. In this situation, the refrigerator is kept at 38 degrees. So let's just say this point is 38 degrees. Okay. So eventually the lemonade will become 38 degrees, same as the refrigerator. But in the beginning, when time equals 0, it was placed in there while it had a temperature of 75 degrees. So in the beginning, the temperature was 75 degrees. Eventually, it will become 38 degrees. Also, we're given that half an hour after it was placed in the refrigerator, it has cooled off to 60 degrees. So this is not going to be up to scale or anything, but I just want to give you a visualization here just to see roughly what's happening. So half an hour later, it has cooled off to 60 degrees. So again, very, very rough graph here. Half an hour later, it's at 60 degrees. And what we want to determine is, when will it be 55 degrees? Again, very roughly speaking, further down here is, so further this way. So let's say that this is the point 55 degrees. We would like to know, when does it happen? Which time corresponds to 55 degrees? So definitely more than half an hour it'll take to cool off to that, because it took half an hour to get to 60. So it'll take, from the moment you put it in the refrigerator, it'll take more than half an hour to get to 55. The question is, how many minutes total is that, or how many hours? Okay, so let's write down everything that's given to us as equations. Okay, so for example, we know that temperature initially at time equals 0, this lemonade was 75 degrees. T of 0 is 75. Half an hour later, so that means temperature at 1/2. Half an hour later, temperature was 60 degrees. T of 1/2 is 60. Now, what is being asked? So basically, temperature at a certain time, an unknown time, T, lower t, is equal to 55. And maybe that's the ideal temperature to have this lemonade. So how many minutes this, or how many hours? We can always convert from hours to minutes. How many hours is it going to take to get to 55 degrees Fahrenheit? So the question then is, what is lower t when the capital T is equal to 55? How many minutes or how many hours does it take to get there? Now, if I use 1/2, which is hours, then my final result will be in terms of hours, and that should be easy to convert to minutes from there if there need be. We can always multiply it by 60. Okay, now let's use the given information one by one to determine C, K, and M. By the way, what is the temperature of the surrounding medium once again? So remember that the object is kept in the refrigerator. So surrounding medium is usually this horizontal asymptote. This is your, in this problem, surrounding medium eventually is going to become 38 degrees. That's where it's kept at, right? So M equals 38. So here's our equation. Temperature at any given time, T equals 38. I'm plugging 38 for M, plus C times e to the negative KT. And let's start using what's given to us, starting right here. At time equals 0, temperature was 75. So go ahead and plug in 0 everywhere you see little t. So, and then set the whole thing equal to 75. So 38 plus C times e to the negative K times 0, and set the whole thing equal to 75. Luckily, we know e to the 0 is 1, so K times 0 is still 0, so e to the 0 is 1. So now what you have is C times 1, which is C. Therefore, we have an equation we can solve for C. We have 38, actually let me just write here, 38 plus C equals to 75. So go ahead and figure out what C is by simply doing 75 minus 38. So 75 minus 38. So we're going to get 37 for C. And now that we have figured that out, we can put it back into our equation. So we already know M, now we know C. Next step, we're going to figure out K so that we can come back and answer this original question. So let's put the C back into our equation and put the M as we know it. So here's what we have. Temperature is a function of time equals 38, which we already knew that part. Now we know C plus 37 times e to the negative KT. At the moment, we don't know what K is, and that's what we're going to get next by using this information. We know T of 1/2 is equal to 60. So how can you use that together with this? If you said, let's plug in 1/2 for time and set the whole thing equal to 60, you were correct. So let's do that. So I'm going to go ahead and plug in T equals to 1/2 into this equation. So T of 1/2 equals 38 plus 37 times e to the negative, K is still the unknown, times 1/2. And set the whole thing equal to what's given, which is 60 degrees. All right, how do you think we could solve this equation? How could we go about solving it? So I need to solve for K. Let me first get rid of this 38. Subtract minus 38 on this side, minus 38 on the other side. So on the left-hand side, you're going to lose the 38. So it's going to become just 37 times e to the negative K times 1/2. Equals 60 minus 38. So go ahead and do that. What is 60 minus 38? You will probably get 22 there. Now divide both sides by 37. So e to the power of negative K times 1/2 equals 22 over 37. And I suggest that for these questions, that we don't round them until the last step. And if you're going to round them, please use lots of decimals, perhaps like 4 or 5 decimal places, so that because you're going to use it in the next level, the rounding gets propagated, the error gets propagated. So let's just try to use as many decimals as possible, or else use exact answers like a fraction. So now to solve for K, I'm going to apply natural log to both sides. So natural log of this side is equal to the natural log of this side, right? So natural log of e to a power, ln and e, they cancel each other. You're going to have just a power, which is negative a half k. Let's call it negative k over 2. And on the right hand side, we have ln of 22 over 37. And now I'm going to multiply both sides by 2 and divide by negative 1. So k equals negative 2 times natural log of 22 over 37. And just be careful when you enter this into the calculator. Ideally, after the ln, you might need another set of parentheses there. So if you do all of this, negative 2 times natural log of 22 over 37, please put that into your calculator. You're going to get something like 1 point something. I'm going to use a lot of decimals. 1.03975. Okay, so we're one step further to the solution. So let's write down what we have right now. So our equation was t of t equals 38 plus 37 times e to the negative kt. So here's our equation. We didn't know k at the time. Now that we obtained k, I'm going to go ahead and put it back in there. So e to the negative 1.03975 t. So this is our temperature equation. This is the equation that models how the temperature changes over time. And remember what was being asked for this question? They wanted to know, when is the temperature going to be equal to 55 degrees? So what I need to do is set the whole thing equal to 55 and solve for t. So my question was, I'd like to know, when is it going to be equal to 55 degrees? Perhaps the perfect temperature for this lemonade. So solve for t. That's what was being asked. So let's do that. Set the whole equation up above equal to 55. 38 plus 37 times e to the negative 1.03975 t equals to 55. So to solve for t, first subtract 38 from both sides. So do a minus 38 on this side, minus 38 on the other side. So here you're going to lose the 38. You're only going to have 37 times e to the negative 1.03975 t equals to 55 minus 38, which will be 17. Now divide both sides by 37, apply ln. So from this point forward, I think everybody knows how to solve for t. So let me give you everyone a few moments to solve for t, and please come back and check your answer. So we're going to apply ln to both sides, and then this comes down, then divide everything by that constant up front. So basically, t turns out to be, so you apply ln to both sides. So applied it here, applied it there, ln of this, you bring the power down, right? And ln e basically disappears. You have negative 1.03975 t equals ln of 17 over 37, and t equals the right hand side divided by that entire constant, negative 1.03975. All right, so take a moment please to figure out what you're getting for t there. And remember, because we entered 1/2 earlier, we assumed time was in hours. The answer you get will be in hours as well. If you got 0.75, you are correct. 0.75 hours from the moment it was first placed into the refrigerator. So basically 15 minutes later, so half an hour later, it was 60, right? 60 degrees. So now we're saying you need about 3/4 of an hour from the moment you place it in the refrigerator. So this was 30 minutes, so you need an additional 15 minutes to get to the 3/4 of an hour, right? So at 15 minutes afterwards, it'll be ready to drink. But typically we leave the answer, unless they ask a specific thing, we're going to leave it from the moment it was placed in the refrigerator, so that's 3/4 of an hour. So if you want to put in minutes, sometimes we convert into minutes, just multiply by 60. And we're going to get 45 minutes. So 45 minutes after the original point when it was placed in the refrigerator, or 15 minutes after we know that it had reached 60 degrees, that this lemonade will be ready to for whoever is looking to get it exactly 55 degrees. For that person, it'll be ready to be to drink. So 45 minutes from the moment it was placed in the refrigerator. Okay, so I'm going to give you another problem to work on. And so that's going to come in the next segment.